Hello everyone, welcome to our discussion of section 2.5 where we will be talking about the chain rule. Now, as you can see on the screen, we've learned how to differentiate simple functions such as the ones that you see on the screen. We did a few examples in section 2.4 video. But what about if these functions are a little bit more complicated, such as the ones that you see in blue ink? What about then? It's in cases like this that a method called the chain rule becomes very useful for us to find the derivative of functions. So suppose we have two functions that are organized in this ways. We have two functions such as these two. We have function y as a function of the variable u. So the function y is a function of variable u, and u itself is a function of the variable x. Okay, so once again, we have two functions such that y is a function of variable u, and u itself is a function of variable x, such that so we have these two functions such that we have a third function, let's call it capital G, that is equal to, that G is a function of, let's see, u. Okay, so G is a function of u, and u is a function of x. So if we want to find the derivative of function g with respect to x, then how would we do that? Because g is not directly connected to x, but it is connected to variable x indirectly through u, function u, right? G is a function of u, but u is a function of variable x. So how do we find the variable of the derivative of variable g with respect to x? That's when chain rule becomes very, very useful to use for us. So according to the chain rule, so how do we find then, given that, how can we find the derivative of function g with respect to variable x? So that's the question. Okay. So according to the chain rule, this is what we can do. Let me move this up a little bit. So according to that, so according to the chain rule, we can say that derivative of function g with respect to variable x is equal to the derivative of function g with respect to u times derivative of function u with respect to variable x. So take the time to just understand the connection between these different functions, because we're taking the derivative of function g with respect to a variable x that is not directly connected to g, but indirectly it is connected to it via function u. So the chain rule is essential in finding that derivative. First, we find the derivative. If this is our ultimate goal, to find the derivative of function g with respect to x, variable x, first we find the derivative of function g with respect to the variable u, which is directly connected to g, function g, then multiply that by the derivative of function u with respect to function x, and with respect to variable x, to which function u is directly related. Okay, so this is critical to understanding this excerpt is critical to understanding the chain rules. So please, if it takes you half an hour or even more to understand what this is saying, it's worth it. Let me add a quick note to this. So now suppose that we have a function y that is equal to, that is a function of variable u. So y is a function of variable u, and u itself is a function of variable x. And this time we have a third function x, which is the x is a function of variable t. Okay? So instead of two functions y and u, now we have three functions. Y is a function of u is a function of x is a function of t. Okay, so we assume that all these functions are differentiable. We've talked about differentiability before, right? Suppose functions f, u, and or f, g, and h, these three functions are differentiable. So if f, g, h, those three functions are differentiable, functions, then to compute the derivative of y with respect to the t variable. Derivative of y with respect to t, so dy dt, we can apply the chain rule. We can apply the chain rule twice in this case. So we'll have dy dt is equal to, because y is not directly a function of t, variable t, so first we take the derivative of function y with respect to variable u, or function u, so dy du, multiply that by the derivative of function u with respect to x, du dx, then multiply that, so that's applying the chain rule once, from here to here that's applying the chain rule once, and from here to the next one, dx dt, this piece is applying the chain rule twice. So this is applying the chain rule once, then from here to here is applying it twice. Like that. Okay, so that's what the chain rule is, and I use this notation, which is the Leibniz notation, as opposed to the Newtonian notation of prime, double prime, triple prime, to show this, the chain rule. So before we see some examples, we talked about the power rule in section 2.4, we talked about the power rule for obtaining the derivatives. So let's connect that rule to the chain rule. So this is pretty important. So the power rule combined with the chain rule gives us this formula. So we have derivative of, let's say, function g of x that is raised to some power. Right? So what if the function has been raised to a power? And so what do we get? We get, since remember we talked about previously, we said that if you have a function f of x, if x is to some power, to find the derivative of this, remember what we did before? We said bring the power down and in front, multiply it by x to the power minus 1, right? This was the power rule for finding the derivative. So we're going to combine that with the chain rule, which gives us this rule. We have n comes in front, so we have n multiplied by that function g of x raised to the power minus 1, right? That's the power rule, times the derivative of the function g prime x. Okay. Okay, so let's see some examples. Let me just remind you that please, as I write down the problem that we're going to find a derivative for, please pause the video and give it your best shot. Write down the derivative of the function as you understand it with the chain rule, and then unpause the video to see my solution and compare your solution with that. This is easy to do with the video, right? Pause and unpause the video. So please do that for each of these examples. All right, so in these series of examples, we would like to find the derivative. Okay, so here is, let's call it part A, or example A. Suppose we want to find the derivative of this function to 100th power. So let's start with something like this, which is a quite easy problem to find the derivative for, especially using the chain rule. Okay, so then we can write, using the power rule, combining the power rule with the chain rule as we just saw, we can bring the 100 down. So this would be f prime x equals 100. And I will use both notations. We need to get used to both notations, f prime and df dx and so on. And at this point, I'm hoping that you've already solved this. You paused the video, you've solved this, and now you're comparing your derivative with this. So we bring the 100 down, multiply it by 4x minus x squared, reduce this by 1, so we get 99 times the derivative of this piece. So let me say d dx, right? d dx of this expression, or derivative. What I'm saying with this notation is the derivative of this expression that comes after it, that. Okay? This is a simple example, but if you follow this fully, you can easily also follow the more complicated examples. But please make sure that you fully understand what happened here. So we applied the power rule, and we're combining that with the chain rule, and the chain rule applies to this piece, not the power anymore, right? We took care of that. We reduced it by 1, which is what we need to do when we find the derivative of a function. So this chain rule then applies only to what's in the parentheses. Okay, so let's write that out. So f prime of x is equal to 100 times 4x minus x squared to 99 power. Now we got to take the derivative of this piece. We know how to do that, right? 4x has derivative 4, minus x squared has derivative minus 2x. Okay, so this is pretty much what we leave it as, like that. So that's the derivative of that, using the combining the power rule and the chain rule. I hope this matches what you found in your own solution. So let's see another one, and we'll call this part B. Suppose we want to find the derivative of this function, f of x, equals 1 over 1 plus secant x squared. Okay? So I don't know about you, but I like to write this with negative power, as you noticed in examples we did in section 2.4. When you write this with negative power, it's easier to find the derivative of, and then at the end we can put these in a form, put the final answer in a form that doesn't have negative powers. It's just in the fraction form, if necessary. So let me do that before I find the derivative. Let's do that. So the function f of x is equal to 1 plus secant of x to minus 2 power. Right? We can do that. Now let's find the derivative, or f prime x is equal to, this minus 2 comes in front, multiplies by all of that, 1 plus secant of x, reduce this by 1, minus 2 minus 1 becomes minus 3. Now we want to multiply this by the chain rule, right? Multiply all of this by the derivative of what you see inside the parentheses. Like that. All right? So let's do that. We have not yet finished, obviously, because we need to take the derivative of this. Okay, so f prime of x is equal to minus 2 times 1 plus secant x to minus 3 power. Now we need to take the derivative of that, multiplied by secant x has derivative. In the previous section we learned secant x has derivative secant x times tangent of x. Like that. So if you've forgotten this, it's no problem at all. Just spend every day. I do forget these too. So the solution is just every day spend 10-15 minutes looking at those previous derivative trigonometric identities and their derivatives that we worked with last time. Look at those formulas, and then every day spend maybe 10-15 minutes to help yourself remember these. Okay, so now we have a negative power here. We can rewrite this in a fraction form so we don't have that negative power, if that's the desire. So we can do that. F prime of x is equal to minus 2 times all of that secant, or I didn't really need this parentheses, but it's okay. Since I wrote it, I don't want to make a mess of it and erase it. But minus 2 times that, and the parentheses is not necessary, divided by that written in with positive 3 powers. So 1 plus secant of x cubed. like that. Okay. Okay, so let's see more examples of these. So suppose we want to find the derivative of this function with respect to t, which is equal to third root of, or cube root of, 1 plus tangent of t. Okay, just like before, let's write this expression in terms of a fractional exponent or rational exponent. It's easier that way to find the derivative. So let's do that first. And the power of the inside here is 1, right? To look at this as a whole group, 1 plus tangent of t as a group, the power of that whole thing is 1. So it will be 1 over 3, which is 3 being the index of this root function. Okay, now we can take the derivative. So f prime t, bring this power in front, 1/3, times all of this. Reduce this power by 1. When you do that, so 1/3, let me use my scratch paper here. I hope you don't mind all of this, but this is just my scratch paper. So we're going to reduce this by 1, 1/3 minus 1. The common denominator is 3. So this is already 3, but this is not. This is 1. We want to multiply this by 3 over 3, right? 3 times 1 gives us the common denominator, but we cannot do this to the denominator and not do the same thing to the numerator. So we have 1 minus 3 over 3, or this will be minus 2 over 3. So we have minus 2 over 3, and then times the derivative of what you see inside the parentheses. So d dx of what's inside the parentheses. I want to take this step by step until you guys get used to it. And once I feel like we've done enough number of examples, then I don't write the d dx anymore. But I want you to know what's going on. Okay, so then we need to take the derivative of this. So f prime t is equal to 1/3 times all of that. Derivative of tangent t is equal to secant squared t. So times, let's see, so times secant squared t, right? Because 1 is just a constant, so the derivative of 1 is just 0, plus tangent t has derivative secant squared t, which is there. Okay, so let's write this, let's clean this up a little bit. So f prime t is equal to secant squared t divided by 3, which is in the denominator already, and we want to write this with positive power. So times all of that. And then, of course, this should be the cube root of 1 plus tangent t squared. Okay, so that is our final derivative of that expression, like that. So on each of these, when you pause the video and you write the solution, and then you compare this, your solution, with my derivative here, if they match, perfect. But if they don't go to you don't want to go to the next example, redo the same problem without looking at my solution, just to make sure that you've gotten the steps down correctly. This is only what you have to do in the beginning when you're being introduced to a new concept. And I'm assuming this is, you're all new to this. But once the wheels get rolling, so to speak, then you don't have to double check so much. Then you know exactly, if something is not matching, if there's a discrepancy, you know exactly what happened. You don't have to solve the whole thing. But in these beginning stages, take it slow and make sure that you understand every single step. Okay, so let's do the next example. Let's call it example D. Suppose we want to find the derivative of y equals cotangent of n theta. Okay, so n theta, that whole thing is the argument of the cotangent function. Okay, so from the previous section 2.4, we know that the derivative of the cotangent function is minus cosecant squared function, right? So minus then, from that, minus, and then 3 is the constant, it stays as it is, cosecant squared of that same argument times, this time we take the derivative with respect to theta, theta being the angle. So d theta of n theta. So we're taking the derivative of what's inside the parentheses. Okay, so we have y prime, move this up a little bit, we have minus cosecant squared of n theta times derivative of n theta, it's like n times x. What would be the derivative of n times x? It would be n. So instead of x, we have theta. So n times theta has derivative n times n. Okay, so now let's clean this up a little bit. So y prime is equal to minus, let me put this, because this is a constant value, like 2, 3, 5.8. So minus n, I'm going to put it in front, and then cosecant, let me not forget the 3 also. So let me put that. This 3 should also be here. Let me put it in a different color, 3, and also 3, minus 3n cosecant squared of n theta. Okay, so that's the final result there. So let's do more examples. That was example D, so this one will be E. Suppose we want to find the derivative of function g of x like that. So we're kind of more familiar with these, right? But still, we have to apply the chain rule. So let's do that. We're familiar with the product rule, though. We saw it before. So we have g prime of x equals. So we're going to bring this, using the power rule for finding the derivatives, bring this 3 down and in front, multiply it by the whole thing, raised to a power minus 1, so that'll be 2, times the whole thing. So derivative of this, using the product rule, remember that? Using the product rule, we take the derivative of this, multiply it by that, and of course we have to apply the chain rule here, because this is x squared, it's not x anymore. So derivative, so 3 times that, times, by the chain rule, we have to multiply by, we have to say d dx of x squared plus 1, the derivative of what's inside the parentheses, times all of that, x squared plus 2 to the 6th power, plus, right, using the product rule, plus the derivative of this times this. So 6 times x squared plus 2 to a power 1 less than that, which would be 5, times the derivative of d dx of x squared plus 2, right, what the derivative of this by the chain rule, multiplied by all of that, x squared plus 1 cubed. Okay, that barely fit across the page, that derivative. Okay, so now let's simplify this and take care of these two. Because we still need to find these two derivatives, right? We need to find this derivative and this derivative, right? Okay, so g prime of x is equal, I'm going to write this as it is, 3 times x squared plus 1 squared. Now the derivative of this is 2x, right? 2x, and then times all of that, x squared, this is x squared plus 2 to 6th power, and plus this one, 6 times x squared plus 2 to 5th power, and the derivative of that again, it would be 2x again, so 2x times all of that, x squared plus 1 cubed. So we found the derivative of that, and we got this here and this here, just to highlight what we did, the difference between the top equation and this one, or the top derivative and this one, is that. Okay. So let's clean this up a little bit, because we can, right? This would be 3 times 2x. Let's make it a little bit more compact. So 3 times 2x is 6x times x squared plus 1 squared times x squared plus 2 to the 6th power, right? That. Let's clean this up a little bit. 6 times 2x is 12x, right? 12x times x squared plus 2 to the 5th power times x squared plus 1 cubed. So if you step back, I mean, we've finished finding the derivative of this. This is done. But if you look at this, if you step back and look at this, there are things we can factor out, right? Can we factor out x? Yes. Can we factor out 6? Yes. Can we factor out x squared plus 1 to some power? Yes, because this is 2, this is 5. So we can factor out x squared plus 1 squared out. Can we factor out, x squared plus 1 squared and x squared plus 1 cubed. So we can factor out this one. Between these two, x squared plus 2 to the 6th power and x squared plus 2 to the 5th power, we can factor out x squared plus 2 to the 5th power. So we can simplify this. Let's do it then. So g prime x is equal to, well, let me write down that factoring the above expression, we have the following. So we have, let's see, so 6x, then x squared plus 1 squared can be factored out, and x squared plus 2 to the 5th power can be factored out. All the lowest powers, the 2 and the 5, can be factored out, which we're doing. So x squared plus 2 to the 5th power factored out. And then, okay, so let's see what do we have left with. To obtain this expression, what do we have to multiply this by to get this expression back? All we have to do is multiply it by x squared plus 2 to power 1, right? That's all. 1 plus 5 will give us 6 again. Then plus, what do we have to multiply this by to get this expression back? All we need is x squared plus 1, and that's it. And well, we also need a 2, right? Because we have 12x, we have 6x out here. So 2 times x squared plus 1. So then let's simplify this expression here. What do we have? We have g prime of x equals 6x times x squared plus 1 squared x squared plus 2 to the 5th power. And if we distribute the 2 inside of that, we get, what do we get? We get x squared plus 2 is x squared plus 2 plus 2x squared plus 2, right? Just distributing the 2 into that. And finally, move this up a little bit. Finally, g prime of x is equal to 6x times x squared plus 1 squared times x squared plus 2 to the 5th power times x squared plus 2x squared, that's 3x squared. 2 plus 2 is 4, and we're done. Like that. Okay. I hope this is starting to make sense, the whole chain rule method. It's a very useful method for finding the derivatives, and you'll see it more and more in the subsequent calculus classes. So let's do another example. So we want to differentiate or find the derivative of this expression, which is s squared plus 1, square root of s squared plus 1 over s squared plus 4. So the first thing we would want to do here is rewrite this with a rational exponent, right? Convert this radical expression into a rational an expression with a rational exponent. It's easier that way to find the derivative. So we say s squared plus 1 divided by s squared plus 4 to 1/2 power and then we can find the derivative, right? So f prime of s is equal to 1/2, put the 1/2 down or in front, times all of this, reduce the power by 1, 1/2 minus 1, it will be minus 1/2, and multiply this whole thing using the chain rule, right? Multiply that by the derivative of what's inside the parentheses. So d dx of s squared plus 1 divided by s squared plus 4. Okay, that's what we want to do. And we've already discussed the derivative for the quotient of functions, right? A quotient. We learned about that in the previous section. The product and the quotient rule for finding the derivative. That's the section 2.4. Okay, so let's do that. So this is all we are left to do. This part is done. So let's write them out. F prime of s is equal to 1/2 times s squared plus 1 divided by s squared plus 4 to minus 1/2 power. Now here comes the derivative of that. Inside the bracket, take the derivative of the numerator, 2s, multiply it by what's in the denominator, s squared plus 4, minus, remember the quotient rule, right? Minus the derivative of what's in the denominator, 2s, times the whatever it's in the numerator, so s squared plus 1. Derivative of the denominator multiplied by the expression in the numerator, and then all of that divided by the denominator squared. So we have s squared plus 4 squared. Okay. Of course, we have quite a bit of simplifying to do here. So let's do that. So we have f prime of s is equal to let's say 1/2 times s, all of that, s squared plus 1 divided by s squared plus 4 to minus 1/2 power, and times 2s times s squared is 2s cubed. 2s times 4 is 8s. Minus 2s times s squared is minus 2s cubed. Minus 2s times 1 is minus 2s. All of that divided by s squared plus 4 squared. Right? So let's simplify that. As you can see clearly that these two add up to 0, right? 2s cubed minus 2s cubed. 8s minus 2s, it's going to be 6s. So let's write that down. So we have f prime of s is equal to 1/2 s squared plus 1 like that, and I should have simplified this, but it's okay, I wrote it down. I'll do it next. And we have times 6s divided by s squared plus 4 squared. Okay, so we can quickly change this to make this positive power by swapping by inverting or flipping the inside fraction, right? Going back to the basic algebra that we did, right? So we have 6s. So by the way, 6s divided by 2, that'll be 3s in the numerator, right? So let's also do that while we're at it. So we have 3s, so s squared plus 4 divided by s squared plus 1. That'll be, I flip the inside, right? Flip the fraction, and that power becomes positive. Then times 6s over 2, it'll be 3s divided by s squared plus 4 squared. All right? So now there's stuff we can do to simplify this expression, right? So let's do that. So, for example, let's break it up first. We can separate that. We can say s squared plus 4 to 1/2 power divided by s squared plus 1 to 1/2 power. That times 3s divided by s squared plus 4 squared. Okay, so you can see that this to 1/2 power and this, we can combine these two and we get 3/2, right? 3/2 in the denominator. So we have, this is the final expression for this derivative. We have 3s divided by, this we can keep, s squared plus 1 to 1/2 power times, combine this one and this one into one expression. So this one and that one, these powers get combined, and we have s squared plus 4 to 3/2 power. Okay, so this is the result of that, combining those two. Plus 4. Okay, so this is as simplified of an expression as we can get it. If you want, you can rewrite this in radical form too. That'll be up to you. Okay. Let's do more examples. I'm counting on you that you're pausing the video before you see my solutions, and you're solving these on a piece of scratch paper on your own before you see these solutions. I trust that you're doing that. Let's see. So that was F, I believe. So this would be G. So suppose we want to find the derivative of this function, y equals secant squared of m theta. Okay. So we have y prime would be 2 times, to bring that 2 in front, times secant with 1 less power, secant of m theta, times the derivative of, inside the parenthesis, let's see, the derivative of secant m theta. Derivative of secant of m theta. Okay. All right. So then we have y prime is equal to all of that. So we have 2 secant of m theta. Derivative of secant m theta is secant m theta times tangent m theta, right? So times, so let me put all of this in a bracket to make it more distinct, and then that derivative is secant m theta times tangent m theta, of course, d dx of the inside the parentheses, m theta. Okay, so we have that to finish. And the derivative of that is just m, right? Okay, so let's do that. So y prime is equal to all of this. The only reason I'm using brackets, if you're wondering, is to separate this piece from what we were finding the derivative for. So this derivative is all of this outside of the brackets. So it's just a visual aid. That's the only reason I'm using the brackets. So 2 times secant m theta times, all I'm doing is taking the derivative of this parenthesis, which is m. So this stays the same though. Secant m theta times tangent m theta times, of course, m. Right? So this expression became this one. All right, so let's, I guess, clean this up a little bit. We have the 2 here and an m. Both of them are constant. Let's put them at the beginning. So y prime is equal to 2m, and then secant m theta times secant m theta. That would be secant squared m theta times tangent m theta. Like that. Okay. I hope this matches what you found on your scratch paper. So next one, let's do an example of this form. So y equals, we want to find the derivative of y equals sine of x, that. Okay? So this would be a good one for you to try on your own and then come back and compare your result with this. Okay, so we have y prime. First of all, we know that the derivative of sine is cosine, right? So cosine of all of that. Then, of course, by the chain rule, we need to multiply this by the derivative of in here, inside. So d dx of sine of x. Okay. And then y prime is equal to, all we have to do is this piece. This piece is already done. So let's write it down. Cosine of sine of x. The derivative of that would be once again cosine of sine of x. So cosine, this sine becomes cosine of all of that expression. And then again, by the application of the chain rule, derivative of sine of x. So d dx of sine of x. Okay, so let's take that. So all of this stays the same. All of this is done. All we have to do is take the derivative of sine of x one more time. So y prime is equal to all of that, cosine of sine of x times that cosine of sine of x times the derivative of sine of x, which is cosine of x. And I didn't need the parentheses, but there you go. Sometimes I get carried away with my parentheses because I like him as a visual aid. So this derivative, this last derivative became that. Okay, can we simplify this a little bit? Let's see. If we can, we'll do it. Cosine, can we do that? No, this should stay the same. That should stay the same. And that, no, we really can't combine any of these. So this will stay, this will stay as it is. So so this is the final answer for us. This is the final derivative. So let's do another example here. That was h, so this would be I. Suppose we want to find the derivative of this expression, y equals cosine of 2 power 4 of sine cubed of x. Okay, interesting expression, isn't it? So we have the cosine function on the outside, which it has a power, and the sine function on the inside, in the argument of the cosine function, has a power itself. Okay, so let's see. Again, please try this on, pause the video and try this on your own, and then come back to the video. I hope you're doing that. So we have y prime is equal to, we have this 4. Before I do that, because we can rewrite this to make it easier to see what we're doing. It's not necessary. It's not necessary to do that, but we could put all of this inside and raise it to 4th power. It's not necessary. We can do it right from here. So we have, let's do it from here. So 4 times, this power comes in front, reduce this, so this is the power rule, reduce this power by 1, cubed of that, sine cubed of x, times, of course, the derivative of all of that, of cosine, times the derivative of the cosine. I'm wondering if I rewrote this at the beginning. Yeah, it would be easier to see if I wrote it differently. So let me do this. This is not wrong, but I want to make sure that everyone understands where, because there are subsequent steps that are coming up, and it's easier if we rewrite this first. So this is not incorrect, but let me just rewrite this first in a different way. So y equals cosine of sine cubed of x raised to 4th power. Okay, so these two expressions are the same thing. But this way, it's easier to see why the derivatives shape up the way that you'll see that they're going to shape up. So now we find the derivative, and eventually we get to that point where I was. But this is easier to follow the work, that's all. So y prime is equal to, bring the 4 down and in front, times cosine of sine cubed x, all of that cubed, times the derivative of what's inside the bracket, which would be cosine of sine cubed of x. That's the piece I'm talking about. Writing this original function in this way makes it easier to follow why we're finding the derivative of this piece in the chain rule. At least that's what I think. It's easier to follow that. Okay, so let's do that. We need to find that, right? But this part stays as it is. So we have y prime is equal to 4 times all of that, cosine of sine cubed x cubed, times the derivative of cosine, of course, is minus sine, right? So times minus sine of all of that, times the derivative of the inside the parentheses. So dx of sine cubed x. Okay. So we have y prime equals, and we have, well, let's find that before. I wanted to combine some things, but this minus with that 4. But let's do it once we find the derivative of sine cubed x, okay, at the end. So we have 4 times all of that, times minus sine of sine cubed x. Now the derivative of that, what would that be? Well, bring the 3 in front and down, times sine squared of x, right? Sine squared, 3 times sine squared x, times what would be the derivative of sine of x? It would be cosine of x. Okay, so now we can simplify this expression and make it more compact. So we have the 4, we have this minus, and we have the 3 here. Minus 3 times 4, we have minus 12. Then we have sine squared x cosine of x. We can, yeah, let's bring that in front. So sine squared x cosine of x. Notice I'm removing the parentheses. It's okay. And then times this piece to the power 3 or cubed. So times cosine. Now we can apply this power to this cosine. So cosine cubed of sine cubed x. So that's that piece, is that. And of course times this. We've already taken care of the minus. So all we have to say is sine of sine cubed x. Like that. Okay, so that's another example. Let's do another example. Suppose we want to, and this would be j. Suppose we want to find the derivative of cosine of square root of sine of tangent of pi x. Okay? All right, so let's rewrite this in terms of a rational exponent. So we have y equals, so this is just rewriting, cosine of sine of tangent of pi x to 1/2 power. So this 1/2 applies to this whole thing, just like the square root. Okay, so now we can find the derivative of this. So y prime would be, let's do this in one shot. So it's now we've seen enough examples that it's easier for us to do that. So bring the 1/2 down. Well, let's see. So, let's see, 1/2. Let's see. So 1/2 the derivative of this. Yeah, we can do that. So 1/2 here times this would be minus sine, right? Times minus sine of all of that. All of that, and let's see, so tangent of that times, I think, okay, so this would be, let me start over, because it would be this way the chain rule wouldn't be so obvious. So let me take the derivative of this before applying the chain rule, actually. So it would be easier if we did that. Yeah, let me do that. So let me start over on this. Sorry about that. So we want to find the derivative of this, j, which is y equals cosine of the square root of sine of tangent pi x. So y, let's rewrite this in terms of a rational exponent, sine of tangent pi x to 1/2 power. So y prime would be, first take the derivative of this. So that would be minus sine of all of that. All of that times the derivative of that by the chain rule. So it's easier to show the chain rule this way. d dx of the inside of all of this piece. So d dx of sine of tangent pi x of 1/2. Okay, that's better. So then y prime would be equal to all of that, which we won't touch, minus sine of tangent pi x to 1/2 power times, now let's bring the 1/2 down. We're taking that derivative, 1/2 times all of that with one less power, 1/2 times sine of tangent pi x. 1/2 minus 1 would be minus 1/2 times the derivative of the inside, which would be cosine of tangent pi x, cosine of that, times the derivative of the inside that parenthesis, which would be secant squared pi of x. So times that, times secant squared, that's the derivative of this piece, secant squared pi x, like that, times the derivative of pi x, which would be pi. So this way, this one I couldn't fit across this screen, but I'll try to maybe make it more contact after that. But maybe the screen seems to be a little bit out of focus, so let me try to focus that. Okay, that's great. All right, now let's try to make this more compact. So y prime is equal to, we have something to negative power, so we want to write that with positive power, and the 2 is in the denominator. So let me do that. So we have this 2 in the denominator. Let's write this whole thing with a positive power, and we can convert it to a radical. Since we've been leaving it as fractional exponents, we can write this with a radical in radical form. So just to get used to different answers. So 2 times square root of that, right? That's the square root, but it's in the denominator, so this would be positive 1/2. So that's why it's the square root of sine of tangent pi x, like that. Okay, and now we have less number of terms for the numerator, which is nice. So then we have minus, let's look for constants and put them in the beginning. So we have a minus here. The 2 is taken care of down here, right? That's 2. That's that 2 times all of that. And then what else? We have a pi here. So let's say minus pi. And then what else do we have? We've taken care of that. Then we have cosine of tangent pi of x. Let's put that also. So cosine of tangent pi of x, pi x, times, let's put that also, secant squared pi x, secant squared pi x, and then we've taken care of these. The pi is in the beginning. We took care of that. We've taken care of that, and then this and this and done, and then we're left with this one, right? So sine of that whole thing, let's use again like the denominator here, let's write this in radical form. So I'm just going to say sine, and that minus is in here at the beginning. This minus is already been taken care of here. So all we have is that sine of all of that in radical form. So sine of this expression, sine of tangent pi x. Okay? All right, so that's the final answer for this piece. Okay, I hope this matches what you have. Although I had to, at the start, I had to start it differently so that the explanation would be clear. Okay, so let's do, what else do we have? Let's do one more example of taking the first and the second derivatives. Let's do that. So let's find, in this example, let's find the first and second derivatives. Okay, so we have this function, y equals cosine squared x. Okay, so we've done this before in section 2.4, but we're going to do it again this time with the chain rule involved, right? Okay, so the first derivative would be y prime. So we want to bring this 2 down. So we have 2 cosine of x. Now by the chain rule, we have that multiplied by d dx of the cosine function, right? That's the chain rule component that we didn't have before in section 2.4. We found the first and the second derivatives, but now we do. Okay, so then the next step would be y prime is 2 times cosine of x. The derivative of cosine of x, of course, is minus sine of x. So the final form, let's clean this up a little bit. Let's organize it a little bit. So this minus and this 2, we put in the front, minus 2 cosine x sine x. Okay, so that's our first derivative. And the second derivative, we have y double prime is equal to, so this constant stays in front, and then let's take the derivative of what's inside. We have the derivative of cosine of x is minus sine of x, right? So minus sine of x times sine of x plus, we're applying the product rule now. Remember the product rule, right? Derivative of this times that, then the plus derivative of that times this. So sine of x has derivative cosine of x times, of course, cosine of x again, like that. So this time we didn't have to use the chain rule. We just applied the product rule, but we did apply the chain rule here. Okay, this was the chain rule to go from here to here. But this is just a product rule. So y double prime is equal to minus 2 times, let me move this up a little bit. So this would be minus sine squared x plus cosine squared x. Okay, and we can distribute this. We don't have to keep this in factored form. So y double prime is equal to minus 2 times that is positive 2 sine squared x, minus 2 times that is minus 2 cosine squared x. Like that. Okay, so these give you a few examples. Please practice with these, as well as the ones we're going to do in class or during the discussion session. Those will give you additional examples that to work with. So once again, I thank you for watching this video lesson until the end. And for now, have a nice day, and I'll see you again next time.